I suppose we shall start recording. Also, let's see how much of that my CPU this takes up. See if everything looks okay. I was recently having a problem. It seemed like a problem with my internet, and it wasn't able to keep up with the upload speed of OBS. So I was quite worried about that, but it seems that everything's working now. We're back in business. Perhaps my internet isn't complete dog doo-doo, so that's great. I'm very happy to learn this. I'm gonna tune in to my own. Keep up with the upload speed of OBS. So I was quite worried about that, but it seems that everything's working now. We're back in business. Perhaps my internet isn't complete dog doo-doo, so that's great. I'm very happy to learn this. That's good. That's good. That's good volume. That's good volume and everything. So I guess let's jump into it. Yeah, let's get started. It seems that everything's working now. We're back. Oh yeah, let me check on Twitch too. Live on YouTube and Twitch. Probably gonna upload to Rumble. You heard? But yeah, so we're gonna be doing some physics. I'm just kind of working through all of my shit that I got going on for school. So we're gonna work some physics problems. We're probably gonna hop over to math. Oh, wait, yeah, this is what I want. Probably gonna hop over to calculus 3, work on some surface integrals, Stokes theorem, Green's theorem. We'll start there, and then we're gonna make our way to the beginning, back to all sorts of stuff. Working with vectors and shit like that, so it's directly applicable to physics, of course. And yeah, all right, cool. So let's I guess let's get into it. I don't really need my headphones on, for sure. Whatever. All right, let's get moving. So four identical charges initially far apart are brought onto a line where they're spaced at 2.5 centimeter intervals. The work needed to assemble this charge distribution is 4.9 kilojoules. All right, so initially we have particles that are really far apart, and then we're gonna make this assembly. So we're going to pull them together. So essentially we got this, and it's 4 identical charges. Yep. Initially far apart are brought onto a line where they're spaced at 2.5 centimeter intervals. All right, so we got our 4 charges. And now they're like charges, right? So like charges are going to repel. We'll make them positive. And so it's going to require work to bring them together. If it were to let them disperse into infinity, then the electric fields are doing work on the particles. But we're doing work on the electric field because we're bringing them together. They're like charges, they repel. All right? So this is what we got, and we're going to have them 2.5 centimeter intervals, 2.5 centimeters. Okay, beautiful. The work needed to assemble this charge distribution is 4.9 kilojoules. So work equals 4.9 kilojoules. Okay, we know our work, and we're going to make a relation between the work and the potential. The potential, which we denotes as V. This is our V, which also has the unit of volts, and so there's a bit of a discrepancy there, but it's nothing too difficult. It's like you become more familiar with these things the more practice you do. Practice makes perfect. So this is our work. We know that work, considering that it's conservative, we're only working with conservative fields. Work equals the negative change of the potential. And now our change in potential, or potential energy, let me maintain this importance of discrepancies. So let me emphasize that this is potential energy, and now we're going to look at the change in potential. The relationship between change in potential and potential energy is that our change in potential, or let's say change of potential, this triangle here, sure, is this even for beginners? Is this my audience? What's really going on here? Perhaps I have no audience, 0 people, so this is for myself. Indeed. All right, this is for myself. All right, divided by the charge. So this is true and accurate. Let's look at our notes here just to confirm. That's the big idea there. Okay, let's look at this relationship between work. So the change in potential equals the negative work, which vice versa, we can say the work equals the negative change in potential. We have this relationship here that the potential energy. Shit. All right, I gotta maintain this discrepancy. I don't want to get you confused because this is very vital when doing these calculations. Okay, So now the change in potential equals the change in potential energy per unit charge. Okay, and then we have a relationship here to the electric field, but right now that is not as important. You know, we know, okay, here, let's, here, we'll keep that page flipped open. We'll keep that flipped open. Okay, set this off to the side. Boom, there we go. Okay, beautiful. Okay, so 2.5 centimeters. Delta V equals delta U over Q. Okay, and then I know that and we're looking for what exactly? The charge. What is the charge? We know the work. So we're given the work, we're given the distance. I know what delta V, so Q times, and so we have to compute it for each individual one. That's the total work, right? To assemble this charge distribution is 4.9 kilojoules. That's in total. Okay. I also know that the potential equals our Coulomb constant multiplied by the charge divided by R. Divided by R. Is the exposure okay? It's a little bright, but it looks fine. Okay. So I know that this is true also. Okay, so I know that the potential is going to be dependent upon, okay, each individual charge. So we're going to have to sum the potentials. Sum the potentials, and then we also have this. So we have V equals this, delta U. Okay, so let's say delta U equals, now we're going to multiply Q. This is the charge, the potential at that charge, and that is the charge itself. So Q multiplied by K, Q over R. Okay, so this is accurate. Now we can say that work equals, we're going to say the sum because each of them contribute their own potential. The sum of the KQ squared over R. Perhaps we could have different charges, but considering that they're all the same charge, it doesn't matter. And this is what we're looking for. We're looking to solve for Q. Okay, so now we have the total work, and it's going to equal the sum of the potentials. The potential energy, the sum of the potential energies, which we derive through our relationship of potential to charge and stuff like this. Okay, so now given this relationship, we can go ahead and compute each individual potential or potential energy. Should we just jump into the potential energy? Perhaps. So we're going to say that we'll start here. We'll say Q1, Q2, Q3, Q4. Okay, we'll consider it like this. Okay, so now the potential Q1, Q2. So we'll say, okay. So we'll say, yeah, shouldn't we? Based on that, and then we multiply it by him. Okay, so we'll go ahead and say that, U1 equals, Q2 times KQ1 divided by 2.5 centimeters. Okay, U2 equals the contribution. Okay, so yeah, to assemble this charge it took nothing. To assemble this charge it took this energy. To assemble this charge it's going to take this guy and this guy. So to assemble him we have Q3 K times, we can go ahead and just add them, which these are going to get pulled out because these are constants. K3 times the potential from Q1, which is now 5 centimeters, plus the potential from Q2, which is only 2.5 centimeters. Okay, U3 equals, okay, Q4 and the contribution from every other charge. So we have Q1 over 7.5 centimeters plus Q2 over 5 centimeters plus Q3 2.5 centimeters. Okay. all the Q's are the same, so to label them wasn't necessary. But for the purpose of like actually showing what I have going on here, because it is important to recognize. All right, and the stream cut out. That's fucking fire. Just dropped to 0 kilobytes per second, and that's amazing. But I guess the recording is still going, so at least that's consistent. Alright, cool. I mean, we're back online now. Hopefully that doesn't happen again. I'm not sure why that shit happens. Garbage internet. I mean, that's really all I could... It just freezes. Is that it? Okay. Alright, very well. Cool. This is the first time back in a long time, so this is great. Okay, so this is what we're looking like thus far. So now let's go ahead and compute this, or rather we could just say, so all these Q's are the same. Right, we have these. So all these Q's are the same. So now if we say that U1 plus U2 plus U3, so we're going to say K2, K1, Q1. Okay, so we'll say, okay, I'm just going to put Q because it's all the same. K, Q, 2.5 plus Q, K, Q over, K, Q over 5 plus Q over 2.5 plus Q, K, Q over 7.5 plus Q over 5 plus Q over 2.5. Okay, so just like this. All right, distributed, property of distribution, or law of what the fuck, what would you consider it? Property, distribution property, something like this. Anyways, we're gonna pull out the Q and the K again. And then we're just going to simply have our additions. 2.5 plus Q over 5 plus Q over 2.5 plus Q over 7.5. Blah, blah, blah. Fucking boring. You know, we get to the point. Forgive me for my cursing. Perhaps I might have children trying to learn more advanced physics. But hey, if you are, then genius. I love it. I love to have you here. So let me not curse. All right, so considering this... And we're solving for Q, so again, distribution property, we're going to have, okay, so Q squared times K multiplied by, you know, the reciprocal, or, yeah, the reciprocal of all of these, 2.5 plus 1 over 5 plus 1 over 2.5. Perhaps I could have done that step sooner, but 7.5, 1 over 5 plus 1 over 2.5. Okay, super cool, super fun, right? We're having lots of fun with this. A little bit later, I'm gonna be continuing with this. We're gonna get to build up in order, like magnitude of the advancement of physics. We're gonna hit Gauss's law. We're gonna get into Faraday's law of electromagnetism, Ampere's law. We're gonna look at all of this, and then we're gonna actually look at the full Maxwell's equations. Okay, so stay with me. Right now, we're just starting at the beginning. We're gonna make our way there. So in reality, it should be a great stream. Okay, so it's looking like this is what we have here now. So let me go ahead and compute this. Plus 5 plus 2.5 plus 7.5 plus 5 plus 2.5. Okay. And remember, okay, so this is what we get, 1.733. And now remember that's in centimeters. So when we do the final calculation, I guess personally I always convert into the correct units, which like is meters in most cases. Is it meters? And in particular to what you're working with, you know, if we're working with coulombs, for instance, a lot of time you'll see microcoulombs, and if you're dealing with microcoulombs, you're gonna want to convert that by saying, you know, whatever the magnitude is times 10 to the negative 6, because this negative 6 represents the micro. And when we're dealing with units such as like electric field, it's newtons per coulomb, not per microcoulomb. Although you could stay consistent in your units, it's just for me, I find it much easier to do the conversion. So anyways, just remember that that's in centimeters. Okay, so now we have this. Oh, wait, actually, that's 1.733. That's not the inverse. I didn't do that correctly. That's 1.733. Wait, that would make sense. 2.5. Did I do that right? Wait, 2.5 plus 5 plus 2.5 plus 7.5 plus 5 plus 2.5. Wait, that's not correct. What the heck, guys? I don't know how that happened. I must have missed something. Anyways, 1 over 25. That's what we're going to get here. 1/25 centimeters, which also equals 0.04 centimeters. Accurate? Shoot, I believe so. Okay, anyways, so now Q squared times, okay, this is 1/4 pi epsilon naught. This is what the K constant equals. This is the Coulomb constant, or electric constant, I believe it's also called, but we can represent it by 1/4 pi times epsilon naught, where epsilon naught is the permittivity of free space. Okay, times 0.04 centimeters. So we'll represent this in meters, which I will say, I'll write it like this, e to the -2 meters. Just like that. All right, I think we're on the right path. Let's hope so. And now, what is the permittivity of free space? Shit, guys, I totally forgot. So let's take a gander here. I'll show you over here. Okay. Whoops, party.com. Permittivity of free space. All right, let's check this out. This is what it is. Okay. So let's put that down. We'll say epsilon naught equals, here, let me pull you back here. Whoops. Pull you back here. Okay, so we'll go ahead and say epsilon naught equals 8.85. It's an approximation, and that's good enough. 8.85. Obviously, you know, the more decimal places you have, the greater the accuracy, the greater the precision. So yeah, just keep that in mind. See, look, you even saw there that the units of this are in meters, kilograms, seconds, amps. Okay, so there's no m to the -3. Oh no, that just means meters cubed because we're talking about a volume. Anyways, 5.4. Okay, e to the -12. All right, I had that memorized. I can't believe I forgot. I had this sum I need to get memorized again. Okay, so this is what we have. So now let's go ahead and do the computation of the full thing. 0.04. Let's see, is that gonna render? Is the exposure too high? E to the -2 divided by 4 times pi times 8.85 e to the -12. All right, this is what we get. So now we have this. Okay. And so now we should say that, and we're going to say 4.9 kilojoules equals Q squared times this pretty big number, 359. Here, let's also put it into scientific notation. 3.597. 597 e to the 1, 2, 3, 4, 5, 6, e to the 6. What are we working with here? So let's take a gander. We just did meters. Oh man, this has a ton of units. To cancel that out, forget it. I'm not gonna do the units right now. Perhaps is necessary. Okay, so now we can say that Q equals the square root of 4.9 e to the 3 divided by 3.597 e to the 6. So square roots of 4.9 E3 divided by 3.597 E6. Square root. Fuck. Okay. What the hell?